Alright, so I kind of got cut off on the last video. I've got cut off right when I was calculating this. So the answer, when you put everything in here, turns out to be negative 123 point like 1.5. It didn't need 1.5, and that's of course in kilometers per second. All right, so all right, so that completes number 7. Remember, of course, and I mentioned this in the last video, the negative indicates that it's blue shifted, it's moving towards us, and we always, or typically, we put this in kilometers per second. It's fine to put it in meters, to put the speed of light in meters per second. Then this would have three more zeros. You move the decimal place three places to the right. All right, so let's do number 8. All right, so number 8 here is very all these are similar to homework problems. So we have a star at the furthest edge of its galaxy is 21 kiloparsecs from the center of its galaxy. Its speed is measured to be 225 kilometers per second. Find the mass of the galaxy in solar masses. And notice we're given that 1 parsec is 206,265 astronomical units, and we also know that 1 kiloparsec is 3.1 times 10 to the 16th kilometers. All right, so the thing about this one is we've got to do a couple of conversions here. One of the conversions is to get R in astronomical units. All right, so to do that, here let's do that first, and then what we're going to do is we're going to use a separate equation. Remember, let me write that equation right now. So the velocity of something that's moving in a circle is equal to 2 pi times the radius. This is any general circle. This is true, divided by the period, right? And so you rearrange that equation, and the period is simply 2 pi times the radius divided by the velocity. All right, so our velocity, notice, is given to us in kilometers per second. So R here, we're going to need R to be in kilometers to cancel the kilometers in the denominator. And then, similarly, up here, over here, for using this combined mass, I'll just remind you that's what this equation is. This is just Kepler's third law for combined masses. But the mass of one particular star in a galaxy full of billions of stars, hundreds of billions of stars, is the mass of one star is insignificant. So that we forget about the one particular star. So this is the mass of the entire galaxy in solar units. So it's some number times the mass of the sun, and that's equal to the distance the star is from its center in astronomical units. Now we have to cube that, and then the period has to be in years. All right, and we square that in the denominator, and so that'll come out to be some number, and that number will be, again, something times the mass of the sun. Now, the key thing, this is like I said, a lot of conversions. The velocity here is in kilometers per second, and then of course if we change R to kilometers, the kilometers cancel, but the period is in seconds. Then you have to convert the period into years, right? So when we do this problem, this is the answer is going to be in some number of seconds, but that has to be converted into years. All right, so just keep that in mind. All right, so several things that we have to do to do this particular problem. All right, so I'm going to go to the new screen here. All right, and here, let me do this real quick. I think this is still in the buffer. Yes. All right, so you can see there's the problem. Hold on, I Probably should have paused it while I was doing this. All right, so what this does for us is it allows us to just to see the problem again. All right, so same strategy. I just showed you the strategy. So let's convert 21 kiloparsecs. Okay, so that's R. So 21. Now kiloparsecs is that would be 21,000 kilo. Kilo, of course, is just thousand parsecs. All right, and now I'm going to convert it to astronomical units. All right, so I know that one parsec. So from what's given, one parsec is 265 astronomical units. All right, so that we need that, of course, because we're going to use that in that combined mass equation. All right, so let me pause it so I can do this in my calculator. All right, so I just calculated this. So this turns out to be 4.33. I'm using scientific notation here because it's a really big number, times 10 to the 9th astronomical units. All right, so we're going to use this in the combined mass equation. But we also need to change R from kiloparsecs. So let me redo this. Remember, this is the one for the period, so R is 21 kiloparsecs, and we know that 1 kiloparsec is approximately 3.1 times 10 to the 16th kilometers. So we'll do the conversion here. So this is 1 kiloparsec. Is approximately 3.1 times 10 to the 16th kilometers. All right, so that's going to put us in kilometers, and the kiloparsecs will cancel. All right, and that turns out to be, and let me pause it while I do the calculation. All right, so I just put this in my calculator. I get 6.51 times 10 to the 17th kilometers. All right, so now we need to use that number. Here, I need to go to a new fresh slide here. We need to use that number in the equation for the period, right? Just to remind you, the period is equal to 2 pi times the radius, and that's why we had to convert it to kilometers divided by the velocity, right? And of course the velocity was measured in kilometers per second. All right, so anyhow, this is equal to, hold on, let me pause it. All right, so if we put in what R is in kilometers, so it's 2 pi times 6.51 approximately times 10 to the 17th kilometers divided by the speed of that particular star in the the farthest part of this galaxy, which turned out to be that was given to us in the problem of 225 kilometers per second. We get, notice of course the kilometers cancel here, right? Kilometers cancel kilometers, and so you get 1 over seconds. So the seconds comes up to the numerator, so you get approximately 1.82 times 10 to the 17th seconds. But remember, we have to convert that to years, right? To use that in Kepler's third law, or for combined masses. So this is going to be 1.82, which I still have in my calculator. So times 10 to the 17th seconds, and then it's the same story as usual, right? You divide by 60 seconds, and then you divide by 60 minutes. I'm not putting in what the numerator is, but it's pretty obvious what this is 1 minute, this is 1 hour, and then of course there's 24 hours in 1 day, and then of course there are 365 days in 1 year, right? 1 year. That's the year is the only thing that remains. And so when you do that, let's see, what did I get? I get a period of, so I'll put it down here. The period that I get is 5.76. Come on, that didn't come out right. That's supposed to be a 5. 5.76 times 10 to the 8th years. Right, so that's the period of this star going all the way around its galaxy, right? So we're going to use this number, this 5.76, and if you remember before, we figured out what the distance r was, which was given to us as like I think it was 21 kiloparsecs, but that was 4.33 times 10 to the ninth years, right? I'm sorry, 4.33 times 10 to the ninth astronomical units. All right, so now let's put it all together. And just give me a second here. All right, there we go. We're going to put it all together, and so the mass of this galaxy is going to equal. So remember what we're doing here. This is simply r cubed over p squared. Now it was a lot of work to get there, right? So r was in astronomical units 4.33 approximately times 10 to the ninth. Remember that's AU, astronomical units, and we have to cube the whole thing, and then we divide by the period, which I just figured out in years was 5.76. That's supposed to be a 7. 76 times 10 to the 8th times 10 to the 8th years, right? But of course, since it's in the denominator, we have to square that, right? Because that's the period. And the answer, let me put this all in my calculator. So I just put this in my calculator. I cubed the numerator, squared the denominator, and I get approximately 2.44. It depends on how you round this. 2.44 times 10 to the 11th. 10 to the 11th times that's the 11th, times the mass of the sun. All right, so that's that would be the end of that particular problem. All right, I'll try to do the last one in the few seconds or a few minutes I have remaining. Let me pause this. All right, so here's our last problem for our practice problems for test 3. Number 9, it says a binary star system is observed. The stars are 14.3 astronomical units apart and take 39.6 years to complete one orbit. Find the combined mass. And so I've written the combined mass equation. Remember, it's little m plus big M. You don't know which one is little m, which one's big M. Is equal to a cubed, right? So in the last thing for galaxies, that a became the radius of the galaxy. But since this is just the distance between two stars, we just use a as the symbol. A cubed divided by p squared. A has to be in astronomical units, which it already is. So I put the 14.3 astronomical units. I cube that and then divide by the period, which is already in years, 39.6 years, but we got to square that. So I put that in my calculator, and I get 1.86. So 1.86, and remember, for the combined mass equation, this is going to be in solar masses. So that's 1.86 times the mass of the sun. So that's times the mass of the sun. Remember, one last quick thing before I finish this. The mass of the sun, I don't know how well this is going to come out. It can sometimes be written like this, the mass with a little circle with a dot in it. It doesn't matter whether you write subscript SUN or the little subscript with the circle with the dot in it. All right, so that is it for the practice problems.